In this video, we'll develop our first learning algorithm called linear regression. In particular, in this video, we'll talk about how we represent the linear regression model. Hopefully remember our earlier motivating example of when we had a set of housing prices and we could plot the data set like this, and we wanted to predict the price of a house as a function of the size of the house. And this was a supervised learning problem because we were given the right answer, or the correct price for each of the houses in our data set. And this was a regression problem because we wanted to predict a continuous value attribute or continuous valued price. Now, let's formalize this problem. Let's see. To formalize this problem, what we're given as data is what we call a training set, where, for example, we may know the size of the house in square feet and the price of the house in thousands of dollars. And so this is again data from Portland, Oregon. And so our first house in the training set may have 2,104 square feet. The second house, the third house, the fourth house, and so on. And for each of these houses, we also know, that went for $400K, that went for that price, and so on. And I'm going to introduce a bit of notation that we're going to use throughout this and later videos as well. First piece of notation is I'm going to use lowercase m to denote the number of training examples. So that corresponds to the number of rows in this table. For instance, for this particular data set, we actually had examples of 47 different houses. So the number of training examples will be 47. I'm going to use lowercase x to denote the input variables, which we also call the features. So in this case, x would be used to denote the size in square feet of the different houses. And I'm going to use y to denote the output or the target variable, which we're trying to predict. Okay? So, one pair x comma y would be one training example. And I'm going to use the notation xi comma yi with i's in the superscript like that to denote the I training example. So that's I training example. And so this x superscript I, y superscript I, this is not exponentiation, right? So this is not x to the power of I, y to the power of I. Instead, this xi, yi, that's just an index into one of the rows of my training set. Or that's the I is an index into one of the rows of this table. Supervised learning thus proceeds as follows. We start off with a training set, which we just saw. And the training set is fed as input to our learning algorithm. Right? It is then the job of our learning algorithm to output a function, which by convention is called a hypothesis and is denoted by a lowercase alphabet h. And what the job of the hypothesis is it takes as input the living area, new living area, or the living area of a new house. By new house, I mean just the house that we haven't seen before, and takes as input the living area of a house that we haven't seen before in the training set, and it's the job of the learning algorithm to output the estimated price. So this function h, called the hypothesis, it maps from x-axis two y's. And the term hypothesis, you know, you may have seen the term hypothesis used in various scientific contexts before. I wouldn't worry too much about what it means. It's just what we call it by convention, and there isn't really any deeper meaning to why we call this a hypothesis and something else. Right. So, in designing a learning algorithm, the first decision we must make is how do we represent the hypothesis, or how do we represent H? For this video, in fact, our initial choice will be to represent H as a linear function, technically an affine function. I'm just going to call it linear. I'm going to say that H of x is going to be some theta 0 plus some theta 1 times x times the size of the house. Okay? And this, of course, corresponds to fitting a linear function, right? Where if this is x, or the size of the house, and this is y, the price of the house, this sort of function, of course, corresponds to fitting a straight line to your data. In a slightly more general case, maybe we know the number of bedrooms in a house as well. So maybe in a more general case, maybe we have more features. Maybe we know the number of bedrooms as well. And in that case, we might use x1 to denote the size of the house in square feet, and x2 to denote the number of bedrooms. So we have two features with which to predict the price of a house. And let's see, in order to do this, of course, we need to go back to our training set and add the number of bedrooms as well. So going back, here's our old training set, and I might add a new column here with the number of bedrooms. And in our data set, this was what? 3, 2, 3, 2, and so on. And so we now have two features, the size and the number of bedrooms with which to try to predict the price of a house. And using this sort of representation, we can then write our hypothesis as h of x equals theta 0 plus theta 1 x1 plus theta 2 x2. Okay? And just to add a bit more notation, this h of x sometimes going to write as h subscript theta of x, where if I want to make explicit the dependence of h on these numbers, theta 0, theta 1, theta 2 as well. And you know, depending on whether we need to make this explicit, sometimes I write h of x, sometimes I write h subscript theta of x. And just to make this notation even a little bit more concise, let's see, for conciseness, I'm going to define x0 equals 1. So it's a feature, if you like. You can think of this as a new feature that always takes the value 1. And so I can write h of x as sum from I equals 0 to 2 of theta I xi. Okay? Or let me cancel out 2 and just write n there, where I'm using n to denote the number of features, which is going to be 2 in this case. And so this lowercase n is I guess the last new symbol I'm going to introduce today in this video. And if you remember your definition of matrices and vectors, if we think of theta and x as vectors, so if you think of theta as a vector, right, theta 0, theta 1, theta 2, and you think of x also as a vector, x0, x1, x2, then this formula over here, this is just, right, theta transpose x, right? Because if you remember from so I guess linear algebra, theta transpose x would be given by, you know, this is theta transpose, theta 0, theta 1, theta 2, and then times the column vector x, x0, x1, x2, and when you multiply theta transpose and x, you end up with exactly this sum over I of theta I xi. And so this gives us a more compact way to write out the form of the hypothesis. So theta 0, x0 plus theta 1, x1 plus theta 2, x2, where we've defined x0 to be always equal to 1. So this completes our definition of the form of the hypothesis we'll use in linear regression. Namely, we're going to use this sort of a linear function to predict the price of a new house. And in the next video, we'll talk about how to come up with these numbers theta that will govern what predictions our algorithm makes.